Hello, we'll be talking about the chemistry of carbon and its compounds, and this is part one. This will review IUPAC naming, it will talk about isomers, and it will give an overview of carbonyl compounds. Later videos, part two and on, will talk specifically about aldehydes, ketones, and the like. The assessment criteria for this unit is to understand and be able to work with IUPAC nomenclature extended to more complex compounds, including cyclic, aromatic, and heterocyclic compounds. In grade 11, we did IUPAC nomenclature when we first started talking about alkanes, alkenes, and alkynes. We'll be able to draw and build structures which show geometrical and optical isomers. We'll know that isomers that are optical will rotate the plane of polarized light. We'll look at the effects of chemical reactions on stereoisomers to include the process called racemization. We'll appreciate that stereoisomers may have different effects on living creatures and systems. We'll know and understand the structure of the carbonyl group, and we'll recognize and be able to name and write formulas and structures for a wide range of carbonyl compounds. Let's start with the first assessment criteria. Be able to work with IUPAC nomenclature. IUPAC nomenclature is similar for cyclic compounds to those that we've already studied. The ring portion of the molecule serves as the name base. As you can see at the bottom of this slide, cyclobutane is a cyclic compound, and the prefix cyclo is used to indicate the presence of a ring. Alkyl compounds attached to the ring are named in the same manner as we would with alkanes. Numbering used in locating groups follow the rules below. If there's just one ring group, as you see in the picture below, it's not necessary to locate it by number. So that is cyclobutane with a methyl group, or methyl cyclobutane. When two ring groups are present, the carbon atoms in the ring are numbered alphabetically by the name of the functional group. So if there's a methyl and an ethyl group, the ethyl group would be labeled first. The lowest letter in the alphabet has the lowest number. When three or more ring groups are present, the ring numbering begins at that location that leads to the lowest set of location numbers. So you can see, for example, the simplest way of naming a cyclic compound, cyclobutane, and with one alkyl compound attached, methocyclobutane. The next assessment criteria is to be able to draw and build structures which show geometrical and optical isomerism, and know that optical isomers will rotate the plane of polarized light. There are two kinds of isomers. They are constitutional and stereo. We'll take a look at a flow chart on the next slide that gives you a little bit better picture of this. But isomers are possible for cycloalkanes that contain four or more carbon atoms. For example, C5H10 has 5 isomers, 1 based on a 4-member ring and 3 based on a 3-member ring. Stereoisomers are isomers that have the same structure and molecular formulas of atoms in space. Cis-trans isomers are isomers that have the same molecular and structural formulas, but different orientation in space. For example, cis means on the same side, trans means across from. We did this last year. Optical isomers, or another name for them, enantiomers, are isomers that rotate the plane of polarized light based upon their concentration and their identity. So if you put polarized light through a liquid of this enantiomer, it will rotate the plane that polarized light comes out of the solution. They are labeled plus or minus. These optical isomers, or these chiral enantiomers, if they rotate plane polarized light in a clockwise direction, they're called plus. If they rotate it in a negative direction, they're called negative. There's a short video from Surrey University that reinforces what I just said about the definition of optical isomers.
Optical isomerism. Organic compounds containing a carbon atom to which 4 different atoms, or groups of atoms, are attached are called chiral compounds. A mirror image of a chiral compound cannot be superimposed on the original. It is called an optical isomer. These isomers have identical melting and boiling temperatures, densities and solubilities. However, they differ in their chemical reactivity. Optical isomers are sometimes called right or left-handed because hands are also mirror images which cannot be superimposed. In biochemistry, nearly all amino acids are chiral, and therefore any proteins, hormones and enzymes derived from amino acids are also chiral. This amino acid is alanine, a hydrogen atom, a methyl group, an amino group, and a carboxylic acid group attached to the same chiral carbon atom. Alanine has 1 chiral carbon atom and therefore just 2 possible optical isomers. More complex biological compounds may have more. For example, morphine, a naturally occurring opiate, has 5 chiral carbon atoms and 32 possible optical isomers. Fortunately, nature is so efficient in biosynthesis that biological systems produce only 1 optical isomer of any chiral compound. Optical isomers may react to form different products, and these can differ widely in their physiological or pharmacological efficacy. One of the best known examples is thalidomide, a drug synthesized in the 1950s by a process which resulted in a mixture of equal quantities of 2 optical isomers. Whilst one isomer reduced the effects of morning sickness in early pregnancy, the other isomer produced tragic side effects, damaging the unborn fetus. As a result, much tighter legislation now controls the production and testing of any optically active drugs.
As I said, let's look at these logic charts. There's 2 here. Look at the one on the left first. Constitutional isomers are non-optically active isomers. There's 3 kinds. Skeletal, different carbon arrangements and different hydrogen atom arrangements. Positional, isomers that differ in the location of the functional group. Functional, isomers that contain different functional groups. Remember, isomers have the same number of carbons or whatever the elements are. Stereoisomers are optically active. Enantiomers are stereoisomers that are mirror images of one another. They're usually indicated by a D or an L, or a plus or a minus. Diastereoisomers are not mirror images, but still optically active. Cis and trans isomers are an example. And then there are other diastereoisomers that have two or more optically active sites. That means a mirror image in more than one chiral center. Understand the effects of chemical reactions on stereoisomers, including racemization. Racemization is changing from one enantiomer to more than one enantiomer. Substitution reactions are an example of reactions that proceed through a carbonication intermediate, and they lead to non-stereospecific addition of substitution, which causes racemization. Unimolecular elimination reactions also proceed through a carbonication, but they do not result in a chiral center. Rather, they result in what we saw when we talked about trans and cis forms. The rate of racemization from L forms to a mixture of L forms and D forms, or plus and minus forms, has been used as a way of dating biological samples in tissues with slow rates of turnover. This technique is known as amino acid dating. This following video talks about this amino acid dating of archaeological sites around the world.
Hello and welcome back to another Aspects of Archaeology. Now today we're going to be looking at amino acid racemization or racemization. What is that, I hear you cry? Well, it's a scientific observation that is very useful for archaeologists. If there's one thing that archaeologists do in addition to excavation, it's work on our dating techniques. No, not that sort of dating, though many of us would confess to needing as much help as we can possibly get. Rather, I'm referring to techniques which further our reach into the past, the ability to fill in any gaps in our dating abilities and make more objects useful for dating archaeological sites. It was early in the 1970s that a new exciting technique was developed. Amino acid racemization, as it was called, could reach much further back in time than radiocarbon dating. It relied upon observations of the change in amino acids in living organisms. This new technique was well received by archaeologists. A new way to date sites is always a good thing. So, amino acid racemization. Want to know how it works? Of course you do. Amino acid racemization can be used to date almost all living things. This is because it is based upon an observation of the amino acids that make up the proteins in all living things. As with many other methods, this dating technique depends on the observation of a change which occurs over time after death. You see, amino acids are important and ubiquitous molecules in living things. Crucially, these molecules have two different ways of manifesting, a left and a right. These molecules are mirrors of each other, which when exposed to polarized light, twist it either to the left or to the right, and in this way, left and right can be observed through scientific observations. Now, crucially, proteins in living organisms contain only left-handed amino acid molecules. This ratio begins to change once the organism dies. With exceptions such as teeth and the lenses of eyes, right-handed molecules are only found in dead organisms. So, over time, after death, the ratio of right-handed and left-handed molecules begins to change, and bit by bit there will be more and more right-handed molecules. And thus we can date the specimen. There are certain caveats, however. This process is extremely sensitive to ambient temperature and air pressure. However, radiocarbon dating can be used to estimate the rate of change on a given site. And with this estimate, we can reach much further back in time than radiocarbon dating alone could do. Thus, amino acid racemization is very useful for archaeologists.
Stereoisomers can have different effects on living systems. We'll just take a look at two in the human body. There is L-carbonate and D-carbonate. L-carbonate has the taste of spearmint, think chewing gum, and D-carbonate has the taste of caraway seeds, the seeds that you find in bread oftentimes, and they're two optical isomers of one compound. The body responds differently to the D isomer and the L isomer of adrenaline. Adrenaline is that hormone that gives you that energy when you're afraid or you're put in a position where you have to produce. The response of the body to the D isomer of the hormone is 20 times greater than its response to the L isomer of the hormone. Adrenaline bonds to its reception site by means of a 3-point contact. The D isomer makes a 3-point contact. The L isomer a 2-point contact. You can see why the D isomer is 20 times greater than in its response than the L isomer. We will, in the following videos, talk about specific carbonyl groups. In this video, we'll talk about a generic carbonyl group that consists of a double bonded carbon to an oxygen atom. You see to the right a picture of the sigma and pi bonds that make up that double bond. A carbon-oxygen bond is polar. The carbon-carbon bond, nonpolar. All carbonyl groups have a triagonal planar structure. That means that between the atoms attached to the carbonyl carbon atom is 120 degrees as predicted by VSEPR. There are many types of carbonyl compounds. One of them is aldehydes. One of the two additional bonds that the carbonyl atom forms must be to a hydrogen atom. A ketone, both of the additional bonds of the carbonyl atom must be attached to other carbon atoms that are part of alkyls, cycloalkyls, or aromatic groups. A carboxylic acid must have one of the two additional bonds of the carbonyl acid atom. It must be attached to a hydroxyl group and the other to a hydrogen, an alkyl, a cycloalkyl, or aromatic ring. Esters, one of the two additional bonds must be to an oxygen atom, which in turn is bonded to the alkyl, cycloalkyl, or aromatic group. And an amide is where nitrogen, in addition to carbon, hydrogen, and oxygen, is present. In an amide, an amino group replaces the OH of a carboxylic acid. Again, we'll talk about these specific carbonyl group compounds in the following videos. I do have some questions to start your thinking, however. I'd like you to look at these questions, answer them, provide me the answers when requested. Thank you.